let's graph this in decimals real quick. So the way I'm going to do it in decimals is I'm going to create a point, and the point is going to be, well, its x value is going to be the x equation. So that's 1 plus e to the 2t. And the y value of the point will be the y equation, which is e to the t. Now here, it only has values of t being in between 0 and 1. But if we want t to be, well, all real numbers, we can make it negative infinity to infinity. And of course, I'm just like picking a really large number just so the calculator can display it. And that's kind of acting as infinity. But you can kind of see what happened when I typed in negative 10,000 versus negative 1,000. At some point, the number was large enough where it displayed the whole end of that part of the graph. So it's looking like it's a square root function shifted to the right by 1. Something like that. I'm going to graph the other ones just so we can see. So let's see, the next one here is 2 cosine of theta for the x value. Okay, 2 cosine of theta. You know, I'm going to use t. Actually, that's fine. Let me use theta. Let's see how it works. So 2 cosine of theta for the x value. The y value is 1 plus sine of theta. Yeah, see, here's the problem with theta. It doesn't actually give you options for, like it did for t above. It gave us t is in between certain values. Here it doesn't. So specifically for decimals, we have to let it be t and then change the values for t. So again, here I want t to be any real number. So actually, you know what? It says specifically theta is in between 0 and pi over 2. So here, for this particular problem, t is going to be in between 0 and pi over 2. So we get that. It looks like a quarter part of an ellipse. So we'll kind of compare. And then the third one now, which is 1c. For this one, is going to be parentheses t squared minus 6t. Plus 6t. There we go. Perfect. Hang on. Squared plus 6t. Perfect. There we go. Comma, for the y value, is going to be 3 minus t. Awesome. And here, for 1c, it says that t is in between negative 4 and 1. So negative 4 is going to be the lower bound for t, and then 1 is going to be the upper bound. So we're good. There we go. But there we go. And if you zoom out, we see that that the curve for the third one is kind of like this sideways parabola that stops at a point.
Yeah.
And for the other ones, well, again, on your calculator, if you press mode and go to polar, you can type in these 3 polar equations for 2a, 2b, and 2c. But on decimals, it'll understand what they are as long as you write it in terms of r equals. And they're all of that form, so that's good. So 1a is r equals 1 plus sine of theta. There we go. So it's that cardioid shape.
Yeah.
And then 2 is 2 cosine of theta over 2. Not like that. We need a parentheses, I guess. There we go. Theta over 2. There we go. I forgot to write r equals. Awesome. So we have this like double loop shape. And again, you can just deselect the ones you don't want to show. So if you want to see the one we just did only, it's this image. So it'd be best to create a table like this, where theta is, let's say, 0 pi, I guess we do pi over 2, pi, 3 pi over 2. These are a lot of values, but it's just an example. then 2 pi, and then you would get to, so let me think how that works. It's going to be pi over 2 again, so it's 5 pi over 2, and then maybe 3 pi, and then 7 pi over 2, and then back to 4 pi. So in this equation, again, this is 2b. So r is equal to, in this case, 2 cosine of theta over 2. So again, the reason why I'm going kind of far beyond 2 pi in this particular case is because of the theta over 2 part. So when you plug in theta over 2, well, when you plug in theta, dividing it by 2 will make 4 pi turn to 2 pi, if that makes sense. So let's plug them in and see what we get. So if you plug in 0, you get 2 times cosine of 0. Cosine of 0 is 1, so this is 2. Okay. When you plug in pi over 2 over 2 is pi over 4. Cosine of pi over 4 is radical 2 over 2. Multiplying that by 2 is just radical 2. Cosine of pi over 2, well, let's see. Cosine of pi over 2 is 0, so this is going to be 0 times 2. 3 pi over 2, so kind of just to understand what we're doing here. So on the unit circle, we're going to be looking at these values for cosine. And remember, cosine is the x value of the point on the unit circle. So maybe that'll help us. So I have 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and 7 pi over 4. Good. So again, when you divide these by 2, you get these values here. So now we're at 3 pi over 4. Because when you divide 3 pi over 2 by 2, you get 3 pi over 4. Cosine of that, well, the x value here is going to be negative radical 2 over 2. This one was positive radical 2 over 2. When you multiply that by 2, because the equation has this 2 in front, of course, you get negative radical 2. 2 pi over 2 is just pi. Cosine of pi is negative 1, so that's negative 2. 5 pi over 2 is 5 pi over 4, if once you divide it by 2. So 5 pi over 2 is 5 pi over 4. Cosine of that is negative radical 2 over 2. So that's going to be negative radical 2 after multiplying by 2. 3 pi over 2 for cosine will be 0. So that's 0 after multiplying by 2. 7 pi over 2 will give you radical 2. And then finally, 4 pi, when you plug it into the inside, will be cosine of 2 pi, which is cosine of 0, which is 1. So it'll give you 2 after multiplying. So get this, which I know is a lot to look at, and what this table means. So let's see if we can kind of compare. So I'm going to erase this this unit circle here and actually draw the graph now. So to actually draw the graph, we want to draw a radius for the given angle. So, and this is still the xy plane. So here in red, let me just draw the angles. And I guess we have these ones too, but I'll leave those in black. That's fine. So let's see. So at 0, the radius is 2. At angle pi over, actually we didn't even need the diagonals, but that's okay. So let's see. At pi over 2, the radius is radical 2. So let's just say this is radical 2. All right. And then at pi, the angle is 0. So it seems to be doing this kind of shape here. Seems to be having that kind of motion because it goes from that radius to this radius. And remember, the radius is just the distance from 0. So once we're at pi comma 0, so this third point here, it means that our angle is pi, but the radius is 0, so it's just the point at the origin only. Let me try to do that shape again, just so it looks a little better. But it's moving kind of like something like this. I'm trying to make it round, but it's not coming out right. That looks a little better. All right, so now for 3 pi over 2, that's the angle down here. This is 3 pi over 2. Let's see, the radius is going to be negative radical 2. So instead of going in this direction, it's going in the opposite direction. So it's going to loop back around like that. All right, and then once we're at 2 pi, which is over here, its radius is negative 2. So again, instead of going in this direction, it's going to loop back from here like this. So we start to see the shape that we got from the graph coming together quite nicely. Of course, the points in between I haven't displayed in the table, so you kind of have to take my word for it, the points in between will actually behave. But the whole idea is that the table actually reflects the graph that we got from Desmos correctly. So for this particular exam, it wouldn't be a bad idea to create a table just to kind of show me that you're not just copying down the sketch you see from the computer. But if you just draw the sketch, as long as the sketch is accurate, that's okay. And in fact, that's really just number 2. Because for number 2, I don't really ask for anything else. I just ask for the sketch alone, because sketching these polar curves is a little bit of a challenge. Now, sketching the parametric curve, though, well, that's also a challenge, but I'm also asking you to eliminate the parameter, which the computer can't really do for us. So let me just kind of finish graphing these real quick. So let's see. So, right. So we have one more to do. So this was a 2c, and that was 3 over, I guess I should write r equals, there we go. R equals 3 over, and then it is 3 minus 3 cosine of theta. There it is. And that's a parabola shape, it looks like. So again, if you deselect everything else, you get this. It's a sideways parabola. That's nice. Good. And there are actually ways of justifying that these shapes are indeed the way they are. The only exception in this case is the second one. So 2b, it'll be difficult to actually show because the shape you get for 2b isn't a normal conic section curve shape that we've seen before. Some weird new polar shape. So with the exception of that, I'll show that. I'll show the reasoning why those shapes are indeed those. But for right now, here's what I'm going to do. I'm going to start number 1, and I'm going to eliminate the parameter. So I already graphed them for you, but now I'm going to actually eliminate the parameter. Okay. So for A, we have x is equal to 1 plus e to the 2t. Y is equal to just e to the 2t. Actually, I'm sorry, it's e to the t, not e to the 2t. Let me make sure I didn't. Okay, good. So here's how I'm going to do this one. So this is 2t. So if you square y, if you square both sides, that is, you go y squared is equal to e to the t squared, which is the same as e to the 2t. Then we can plug this in here. Because this, in fact, is e to the 2t, so that means it's just the same as as y squared. So we get this equation here. X is equal to 1 plus y squared, and that's it. We've eliminated the parameter. And in fact, if you solve for y, you go y is equal to plus or minus the square root of x minus 1. And all I'm doing there is subtracting 1 to the other side. And that'll give me y squared is equal to x minus 1. And then when you square root, you get plus or minus the square root. Now, it's a little particular because notice here, for our y equation, y is equal to e to the t, and for all values of t, e to the t is positive. Meaning, if y is equal to the square root of x minus 1, we'll take the positive root only. So in reality, this is y is equal to the square root of x minus 1. And if you graph radical x minus 1, you'll get the same image we got for this graph here. And it's kind of what I said, it's just the square root function shifted over to the right by 1 unit. So that's the image you'll get, and that's the same image we got for 1a when we graphed it. So 1b, x is equal to cosine of, cosine theta. It was 2 cosine theta, there we go. Y is equal to 1 plus sine of theta. And here theta is in between 0 and 0 and pi over 2. This seems a little challenging, but the only way I know to relate cosine and sine is using this identity here. Sine squared plus cosine squared is equal to 1. This is the one equation that comes to my mind where cosine and sine both make an appearance. So we can actually, let me circle this so it's not in our way, we can square each of these. The only problem is that when you square y, well, you'd have to square 1 plus sine, and don't do that, because if you do that, you'll get 1 plus 2 sine plus sine squared. So the problem here is you still have this sine without the power 2. So instead what we're going to do is we're going to subtract 1 and then square both sides. But we'll see that right now. But first let's look at the x equation. So for the x equation, if you square both sides, actually divide by 2 and then square both sides, but whatever the case may be, you'll get this. You get x squared over 4 is equal to cosine squared. Because if you square both sides first, you get x squared is equal to 4 cosine squared. But then if you divide by 2 and then square, you'll still get this. So here, like I said, if we subtract 1 to the other side first, we'll get y minus 1 is equal to sine like this. Then squaring both sides will give sine squared on the right, but y minus 1 all squared on the left. Perfect. And now if you add each of these together, we'll get the following. We get x squared over 4 plus y minus 1 squared is equal to, well, 1. Because sine, let me box this, sorry. Because x squared over, well, because cosine squared plus sine squared is 1. So there we go, we eliminated the parameter theta. I hope that makes sense, because again, the first term here is cosine squared, the second term is equal to sine squared, and cosine squared plus sine squared is equal to 1, so this whole equation is equal to 1. And if you have seen 10.5, or if you just remember conic section curves, this is an ellipse with a center, I guess it'd be 0, 1, and let me see. And I guess the a value is 2 because it's what's over x, or what's under x, the square root of that number. So since 4 is under x, the a value is the square root of 4, which is 2. And it's horizontal because the larger denominator is under x. So it's horizontal. So if you actually graph this, you get this image here. So the center is 0, 1. It's up here. You would go to the left and right by a distance of 2. You'd go up and down by a distance of 1 because the denominator of y is 1. So you get this shape here. Now, the fact that theta is only in between 0 and pi over 2 basically tells me that we're only staying within the first quadrant. So in reality, we'll only get this quarter ellipse here, just like we got when we graphed it. So this again justifies the graph that we got from decimals. All right, I hope that's clear. So now for C, I think is probably the most challenging one, but let's take a look. I don't think it's even that bad. This may involve completing the square, but let's take a look. So here we'll get x is equal to t squared plus 6t, y is equal to 3 minus t. Actually, no, I don't think this involves completing the square at all, now that I see it. Well, let's see. Yeah, so what I'm going to do here, and this is an idea I gave us when we first took a look at parametric curves. You can solve for t in one equation and plug it into the other one. So in this case, we don't want to solve for t in the first equation because there's a square there on t. But for the second equation, if you just subtract y to both sides and add t to both sides, you end up with this. T is equal to 3 minus y. All right, so plugging this into both of these t's, we end up getting this. X is equal to 3 minus y squared plus 6 times 3 minus y. So we can expand this out and then just simplify things. And you'll see it's a quadratic in y, meaning that it'll be a sideways parabola. So a normal vertical parabola is y is equal to a quadratic in x, but if your variables are switched, then it's a horizontal instead of vertical shape. Okay, so I'll expand this out. So this is going to be 9 minus 6y plus y squared. And then distributing this, we get plus 18 minus 6y. So writing this in order, we get y squared minus 12y because these two combine. And then 9 plus 18 is 27. Perfect. And what's actually really nice about this, so this is our answer after eliminating the parameter. What's really nice about this, though, is that if you were to graph this by hand, you can actually factor this in this case as y minus 9 times y minus 3. We all see that those are the two numbers that multiply to positive 27, and they will simultaneously add to negative 12. So what that tells me is that the parabola, well, again, it's a sideways parabola because it's a quadratic in y, and its y-intercepts are at 3 and 9. So if you create a parabola that has those y-intercepts and it's sideways, it'll look like this. So let me shift up 9 more so it looks a little better. Whoops. That's fine. So that's 9. Let me see here. Now, the only thing, though, is that if you notice here, well, t has to be in between negative 4 and 1. So what we can do is we can plug in negative 4 to see what the lowest y value is, and plug in 1 to see what the highest y value is, or vice versa. It just kind of depends. But if t is, let's see. So we had y was 3 minus t. So if t is negative 4, then this is going to be 3 minus negative 4, which is 7. So we'll go y is equal to 7. So y is equal to 7 is about somewhere here, because it's a little lower than 9, of course. So that would correspond to this point, which I think makes sense. It's a negative x value, it looks like. So if you plug that t value into the x equation, you should get a negative x value. But we can just see it real quick. If you plug a negative 4 into x, you get negative 4 squared is 16, and then 6 times negative 4 is negative 24. And that's indeed negative 8, so the x value here will be negative 8. This image, of course, is not to scale, but that's what we end up getting mathematically. And let's see. So it's traveling in. It's still hard to tell what direction it's traveling in. But so I'm plugging in -4. But now if you plug in 1, well, if you plug 1 into y, you get y is equal to 3 minus 1, which is 2. So then the y value would be 2, which is down here. So that's a little lower than 3. So imagine that's 2, let's say. Now, what the x value is going to be, looks like it'll be a positive number. So let's take a look. But when you plug in t to be 1 here for the y equation, you get 3 minus 1, which is 2. But then for some reason, I plugged in 3 for x. But remember, the t value we're plugging in is 1, not 3. So we'll get 1 squared plus 6 times 1, which is 6. So the x value will be 7, not 27. So that was my mistake there.
Okay.
So nice. So it actually does line up with the image we get from Desmos, which is nice. Their image obviously looks a lot better than the image we got here. And all 3 of these images are good too. Awesome. That's r is equal to, it's 3 over 3 minus 3 cosine theta. There it is. Well, let's see. So if we reciprocate both sides here, we get 1 over r is equal to 1 minus cosine theta. And then if we multiply both sides by r, we get 1 over r times r is just 1 equals r times 1 is r minus r cosine theta. So we end up getting this if we multiply both sides by r. And if you add, let me see, I don't want to add anything. Well, let's do this. So we know this is equal to x. We don't know what, well, I guess we know r is the same thing as the square root of r squared. So I guess we could replace it with that. I didn't really want to resort to doing that, but that's something we definitely could do. In fact, that's something we kind of could have done with 2a, but the image just, so the Cartesian equation we would get would just be too wacky. But here I think it actually kind of works. So I hope that's justifiable. But again, r squared is equal to x squared plus y squared. So when you square root, you get r is equal to this. So I'm going to add x to the other side, though. So adding x to this side will leave us with 1 plus x is equal to the square root of x squared plus y squared. Now if we square both sides, we can expand out the left side. We'll get 1 plus 2x plus x squared equals, here they cancel out and you just get x squared plus y squared. And then if you subtract x squared to the other side, there we go. Look at that. So we get 2x plus 1 is equal to y squared, which is actually a quadratic in y. So it's a sideways parabola. So I think that justifies the shape enough. And that's all I really wanted to say. If you recall from 10.5, this particular shape you can write as 2 times x plus 1/2 equals y squared. So the vertex of the parabola is just, well, -1/2 comma 0. The p-value is the number in front divided by 4, so that's 1/2. Or 2 over 4 is 1/2. So you can find the focus and the directrix of the parabola in this case if you'd want. But finding the vertex and the y-intercepts I think are okay enough to just get the graph. But anyways, it's a sideways parabola, and that's exactly what we got here. These are the 3 main things that apply for polar when converting to Cartesian always. X is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared. These are always true. So let's take a look at number 3 now. Let me zoom in a little bit. Okay. So 3 says find the slope of the tangent line to the given curve at the point corresponding to the specific value of the parameter. So really what we're trying to do is find dy over dx evaluated at the given value. So for A, our equation is, or our equations are, x equals ln t, y equals 1 plus t squared, and then the value we have is t is equal to 1. So let's see. To find dy over dx, well, remember, there's actually a formula for this. dy over dx is dy over dt over dx over dt. Now, dy over dt and dx over dt are just the derivatives of those equations, y and x, respectively. Let me make it a little more clear, okay? So dy over dt is the derivative of y with respect to t. So what's the derivative of 1 plus t squared? It's just 2t. Good. What's the derivative of ln of t?
Is that 1 over t?
It's 1 over t. So here, if you multiply top and bottom by t to get rid of the fraction within a fraction, well, we get cancellation on the bottom. So really it's just 2t squared. And then, since we want to plug in this point, when t is equal to 1, we get that our slope is just this, well, 2 times 1 squared, so it's just 2. And that's it. Now, there is another way of going about this, and that's eliminating the parameter first. So I just want to show that real quick. I may not show with the other one, but I'll show it with this one at least. So let me see. So if we solve for t in the first equation, we can take e to both sides. Well, e as both sides as powers of e. So e to the x equals e to the ln of t. E to the ln of t is just t. So we get t is equal to e to the x. If you plug that into y, you get y is equal to 1 plus e to the x squared. I wrote that really weird, sorry. There we go. Y is equal to 1 plus e to the x squared, which is e to the 2x. And if you find the derivative of this with respect to x, you just get 2e to the 2x, because derivative of 1 is 0, and derivative of e to the 2x is itself multiplied by 2 by chain rule. And now, well, we want t to be 1, but there's no t in this equation. There's an x, though. So we figure out what x is when t is 1. Well, take a look at this. When t is equal to 1, well, we have 1 is equal to e to the x. So that means x would be 0, because e to the 0 is 1. So when you plug in x equals 0, what do you get for dy over dx? You just get 2, because e to the 0 is 1. Notice they're the same, right? So I showed 2 different ways of doing that. So let me just write this or this, because I don't say which way to do it on the review. So I hope you found that pretty insightful. I think that was a pretty cool problem. But I'm going to do 3b now. But 3b I'm going to do not the second way, but I'm going to do the first way. In fact, for 3b, it's going to be a little harder, because since it's a polar equation, there's actually a different formulation for polar to find the first derivative. Anyways, let's see if we can do it. So for b, we have r is equal to e to the negative theta. Our theta value is just pi. So we're going to plug that in after finding dy over dx. Now the dy over dx equation for polar it's pretty similar to dy over d theta. Remember, y is equal to r sine and x is equal to r cosine. So the numerator is the derivative of our sine, which requires product rule. So you can check me on this, but it should be dr d theta times sine of theta plus r cosine, where the denominator portion of the formula for dy over dx is dr d theta cosine minus r sine, because derivative of cosine is a negative sine. So I actually forgot the formula, so I don't have it in front of me. But I'm just looking at these two here, taking the derivative of each one using the product rule to get dy over dx. So I hope that's pretty clear. But now we have to plug in to see what these things are. But now let's take a look here. So we know r is this, right? So that means we can actually find dr d theta. So derivative of r with respect to theta is, well, let's see, derivative of e to the negative theta. Theta is our variable we're taking derivatives with respect to here. So it's itself, but by chain rule you multiply by derivative of the power, which is negative 1. So it's negative e to the negative theta is what I'm getting. Okay, so now looking at our equation for dy over dx, I have dy over dx is equal to, so these two right here are just negative e to the negative theta. So we know that. Good. Perfect. Times sine of theta on top plus r. R is what we have circled in red. So r is just e to the negative theta cosine theta. Again, r is e to the negative theta, and then times sine of theta. So just, but you could just plug in theta equals pi right away. But let's see, if you pull out e to the negative theta on top, you have negative sine plus cosine left over. If you pull out e to the negative theta on the bottom, you have negative cosine theta minus sine theta left over, right? Then you can cancel these out. And now we can plug in our theta value, which was theta is equal to pi. So when theta is equal to pi, we get negative sine of pi plus cosine of pi. Now cosine of pi is negative 1, and sine of pi is 0. In the bottom, we get negative cosine pi minus sine pi. So this is 0, this is 0, this is negative 1, and this is negative 1. So we end up with negative 1 over positive 1 because the double negative. So our answer is just negative 1. 4 seems like a doozy. So 4 is asking us to find the first and second derivatives. So dy over dx and d squared y over dx squared. Now, dy over dx, I don't think it's too bad. These are both parametric, by the way. I wouldn't dare ask you to find the second derivative of a polar equation. It'd be way too hard. But let's see, a, we got t plus sine of t, and y is equal to t minus cosine of t. Now, I'm not saying which way to do this, so you could use eliminating the parameter if you'd like, if it's possible. In this case, I don't know how possible it is, but it's something you can try to do if you wanted, but I don't think it's doable in this case. So for A, let me just use our formulas. So the formula for dy over dx, remember it's dy over dt over dx over dt. So in other words, find the derivative of each equation and then divide y's by x. So derivative of y's equation is 1 plus sine of t. Derivative of x equation is 1 plus cosine of t. Do you all see that?
Yes.
Awesome. That's it. That's our answer. But I'm going to write it like this. dy over dx equals, and then I'll write that. Awesome. All right, so now for the second derivative, we're not even done with a yet. We need to find the second derivative. So find the derivative once more. So the second derivative has its own equation, which is really wild. And it's this. By the way, this should have been a dt over dx. No, sorry. Dx over dt is what I meant to say. There we go. So for d squared, for the second derivative, it is going to be the derivative of the top over dt, so with respect to t, and then dividing this by dx dt. You know what? Actually, I made a mistake. This inside should be the derivative dy over dx. There we go. That sounds a little better. So again, just to justify this equation a bit, if you take a look at dy over dx, if you think about what's happening to y only, y is here. So all we're really doing to find dy over dx is taking the derivative of y with respect to t and then dividing that by dx dt. Okay. Similarly, for this one, this is the derivative with respect to x of y prime, which is dy over dx. So that means that this will be in place of y in our equation here. I don't really need to justify it because I've already justified it in a previous video for that lecture. And also, this formula will be given to us attached to the formula sheet. Well, it's on the attached formula sheet. But anyways, here we go. So we want to find the derivative with respect to t of what we just found. 1 plus sine of t over 1 plus cosine of t. So we need to use the quotient rule, yikes, over the derivative of x, which is 1 plus cosine of t. So from quotient rule, let's see if we can recall the quotient rule. So quotient rule will be all over the bottom square. So it's going to be 1 plus cosine of t all squared for the denominator squared. And let's see. So quotient rule is derivative of, so let me just write it here. So for quotient rule, u over v, derivative is u prime v minus uv prime all over v squared. That's a v. So it's derivative of the top regular of the bottom minus doing the opposite way around. So let's see. Derivative of the top, 1 plus sine, its derivative is just cosine, times regular of the bottom, 1 plus cosine, minus regular of the top, 1 plus sine, times derivative of the bottom, which is negative cosine. Sorry, negative sine, negative sine. Yeah, derivative of 1 is 0, derivative of cosine is negative sine. And that's, so this is right here, this is the numerator, and then the denominator, 1 plus cosine of t stayed the same. But in reality, what this really does is it brings another 1 plus cosine of t into this denominator here, making the total power just 3, really. Okay? Now on top, if we distribute, we get cosine plus cosine squared. I don't know if it's worth it to do this, but I'm just going to try it to see if anything simplifies. So cosine plus cosine squared. Oh yeah, this actually, it is worth it to do. So if you distribute this, you'll get negative sine minus sine squared. But if you distribute the negative as well, you end up with negative 1. Well, let me say that again. So we have negative sine of t times 1 is negative sine t, but then distributing the negative leaves us with positive sine of t. And similarly for, in fact, you can just see it like this. The double negative makes it positive. So we don't even need to worry about the sign, in fact. So that actually may be a better way of seeing what I'm trying to justify here. So then we get plus sine of, well, sine squared of t.
And then can we simplify cosine t plus sine t to be equal to 1? Or
Well, well, look, cosine squared plus sine squared is just 1. So altogether we have cosine t plus sine of t plus 1 all over 1 plus cosine of t cubed. Now, the top does have a 1 plus cosine, so you could split it up as 1 plus cosine of t. I keep wanting to write theta over 1 plus cosine of t cubed and then cancel that out. But then you'd have a sine over 1 plus cosine of t cubed. So for that reason, I'm actually not going to do it like, I'm not going to actually do that at all. I'm just going to leave it like this. So this is the answer for d squared y over dx squared. So let me just box this. I'll get rid of that. Awesome. So let me just write down below here. B, our equations are x is equal to 1 plus e to the 2t and y equals e to the t. Over dx. Again, that's dy over dt over dx over dt. So derivative of y's equation is just itself, e to the t. Derivative of x's equation is, well, let's see. Derivative of 1 is 0, so don't write it. Derivative of e to the 2t is 2 e to the 2t. E to the 2t. So yes, there's actually some cancellation we can do here. Basically, you can cancel out by subtracting powers, and what you end up with is the bottom power is 1t less. If that makes sense, because we're subtracting t from the power. Another way of seeing it is that the numerator is 1 times e to the t, the denominator is 2 times e to the 2t, which is e to the t times e to the t. So we get a cancellation of e to the t's, and we're left with 1 over 2 e to the t. It's a different way of viewing that. There we go. So, yeah, so we have dy over dx is equal to 1 over e to the 2t. 2e to the t, and I'm going to leave it like that. Now, it's a little weird because, remember, since e to the t is equal to y, we could actually write this equation as 1 over 2y. So if you wrote that, that would be acceptable as well. Okay? So just kind of keep that in mind. For the second equation, for the second derivative, d squared y dx squared. Remember that that's d over dt of dy over dx. Over dx over dt. So dx over dt is the same original denominator before cancellation, 2e to the 2t. Derivative of dy over dx, well, I guess we'd have to use chain rule. So one way of writing the derivative, so dy over dx, instead of, because we could use quotient rule, but if you wrote it like this, 1/2 e to the negative t, it'll make it easier to find the derivative of with respect to t by considering chain rule. So derivative of 1/2 e to the negative t is itself 1/2 e to the negative t, but times derivative of the inside, which is -1. And now there's some simplification we can do here. So we can multiply top and bottom by 2 to cancel out these 2's. And we can also multiply top and bottom by e to the t to get rid of, well, this negative power here. So we still have -1 left over on top, but the bottom now is 4e to the 3t now, which is acceptable for the second derivative. Also notice, since e to the t is y, this is the same as -1 over 4y, which is, well, 4y cubed, which is also acceptable. In fact, this is what I was saying earlier about converting this to Cartesian. Well, we did this already for 1a, which is nice. So if you wanted to convert this to, well, if you wanted to eliminate the parameter, you would end up getting x is equal to 1 plus y squared. So that means y would be the square root of x minus 1, or x minus 1 to the 1/2. That means dy over dx is 1/2 x minus 1 to the -1/2. And its second derivative would then be -1/4 x minus 1 to the -3/2. So find the area of the loop. The exam version of this is a little easier because I don't think I think for the exam version number 5, I actually give you the, I straight up give you the bounds. I'm not entirely sure, so don't quote me on that. But I just remember that it's a little easier than what this review is. So we have x is equal to c cubed minus 3t, y is equal to t squared plus t plus 1. Now the only thing is we don't know where the loop occurs. You could graph this. I'm going to graph this by hand. And some kind of coincidental things happen. So just kind of bear with me a little bit to see if we can figure out what's going on. So we're going to plug in certain values of t. So I'll start off with 0, 1, 2, 3, and let's see where it goes from there. So if we plug in 0 for t, we get 0 for x and 1 for y. When you plug in 1 for x, 1 for t, for the x value, you get, let's see, 1 cubed minus 3t. That's 1 cubed minus 3, so that's -2 for x. Y will be, I guess, just 3 when you plug in 1. All right, let's see. When you plug in 2 for t, for the x value, we get 2 cubed is 8. 3t, 3 times 2 is 6, so it's going to be 2. Let's see, for the second one, for y, so I'm just plugging it into the equation. So I get 2 squared plus 2 plus 1. So it's 4 plus 2 plus 1, it's 7. Now, 3 I think will be too large, but let's take a look at it. So 3 cubed is 27 minus 9, so it's going to be 18 for x. And then y is going to be 3 squared is 9 plus 3, which is 12, so it's going to be 13. All right, so now what I'm going to do is if we plug in larger t values, we're just going to get larger x and y values. So now I'm going to plug in negative values. And what I'm trying to do here is I'm trying to see where a loop occurs. And if you kind of think about it, a loop would occur if you have the same x and y values, the exact same x and y values. So far we're getting these points. We get 0, 1. We get -2, 3. We get 2, 7. 4, 5, 6, 7. So far it seems to be going like this. And these arrow marks indicate the direction that t is traveling. So this is when t is equal to 0, t is equal to 1, t is equal to 2. Right? So now let's plug in negative values to see if we get anything else here. So when t is equal to -1, for x, what do we get? Let's see, -1 cubed is -1.
Should be -2.
And -1 times -3 is +3, so it's going to be +2.
Oh, 2, okay.
And for y, -1 squared is +1, -1 plus 1 is going to be +1 there. So that's a new point. So 2, 1 looks to be over here. Let me just make sure this is correct. It looks a little funny, but that's fine. So it seems like it has the same y value here, so it probably curves in between. So hopefully the loop occurs maybe here. But let's plug in -2, see what happens. So we plug in -2, we get -2 cubed is -8. And then it's -3 times -2. That's going to be -8 plus 6. That's -2 for the x value. So I'm just plugging in the x and y. So for the, let's see, for the y value, when you plug in -2, you get -2 squared is +4, -2 plus 1. So that's 2 plus 1, that's 3. So we get -2, 3, which is back to this point here. See that? So it actually loops around like this, it looks like. I don't know how much justice I'm doing it, but this is the region we're trying to find. And we actually know our bounds because these points are the same. These points are the same. They both have the same x and y coordinates. So that means t equals 1 and t equals -2 will be our bounds of integration. So now all we need to do, so now we know that, let me just write this. Loop is, let me just say loop occurs for t values in between -2 and 1. So that part was unobvious and that we had to graph. And like I said, for this reason, the exam version of this question, number 5, will be a little more obvious in the sense that I think I'll actually just straight up give you the bounds of integration. So now let's recall the area formula for parametric curves is the integral between the bounds, in this case it's -2 and 1, of, I believe it is, so the way I remember it is it's the integral of y dx. So the y equation is the same, so it's just y of t. But then the x equation, this is dx. And if x is equal to, well, x of t, then dx is equal to x prime of t dx. So this is times x prime of t dx. Sorry, dt. That should be dt. My mistake. There we go. So let's see. So if we look at y stays the same. So this is the integral from -2 to 1 of y, which is t squared plus t minus 1, or plus 1, sorry. And then x prime. What's the derivative of x? The derivative of x's equation is actually not too bad. It's 3t squared minus 3. And then dt. Is that right?
Yes.
Awesome. So now all we have to do is antiderive this. Now it looks kind of crazy. It looks like a product, but we can actually expand it out quite a bit. here's what I'm going to do, just to make things easier for me. I'm going to notice they both have 3 in common here. So I'm going to pull 3 outside of the integral because it's a constant, of course. Also, what we have left over is t squared plus t plus 1 and t squared minus 1. So we can actually distribute then dt. So I'll distribute like this. I'll distribute t squared into each of these first, and then I'll distribute -1 into each of these second. So let's see if we can follow, okay? So we get 3 outside of the integral, -2 to 1 of. So t squared multiplied to everything just adds 2 to each power. Like that. There we go. -1 multiplied to everything just changes the sign of each term. So we end up with this. And then dt. Now there's some combination. Notice these actually just straight up cancel. And now we can just find the antiderivative of each one. So the antiderivative of this, 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 and this are each of the following. So this is t to the 5th over 5. This is t to the 4th over 4. This is -t squared over 2. And antiderivative of -1 is -t. Now we're going to evaluate this between the limits -2 and 1, and then multiply by 3 after the fact. Nice. So when we plug in 1, we get 1/5 plus 1/4 minus 1/2 minus 1. Good. Minus, when we plug in -2, -2 to the 5th is -32. So that's that over 5. -2 to the 4th is positive 16. So that's going to be plus 16 over 4, which reduces, but I'll do that after. And then minus -2 squared is positive 4 over 2. That also reduces. And then minus -2, which I'll write like that, I guess. So a lot simplifies here. Let's see. So here's what I'm going to do. I'm going to notice that these two, well, 1/2 minus 1/4 is 1/4. So 1/4 minus 1/2 is then -1/2, -1/4. Okay? So I'm going to leave those like that. So I'm going to leave it as 1/5 minus 1/4 minus 1. This negative will distribute to each of these. And as previously spoken, the double negative here just makes a positive. And I'm going to reduce each of those fractions as much as I can. So the first term is going to be positive 32 over 5. The second one's going to be -4, and then positive 2, and then -2. We're all okay there? Nope. Now, a lot of things combine. In fact, these two cancel. These two combine to -5. These two combine to 33 over 5. So altogether, we have 33 over 5 minus 1 over 4 minus 5. So we need a common denominator. So there's a lot of arithmetic going on here, obviously. You could just use your calculator at some point, but I think what I'm doing should be okay. So I'm finding the common denominator, multiplying this top and bottom by 4, this top and bottom by 5, and this is 5 over 1, multiply top and bottom by 20. And what we'll end up getting is 33 times 4 is, I think, 132. You can check me on that, but I think that's right. Minus 5 times 20 is 100. All right, so the beauty here is that, well, the large numbers actually subtract quite nicely. 132 minus 100 is 32, and then 32 minus 5 is just 27. And since 27 times 3 is 81, I'm getting 81 over 20 as the answer here. So for 5b, we have r is equal to 1 minus 3 sine theta. Now, it would be helpful for us to look at the graph here, and for this one, I'm going to let Desmos take over a little bit, so we can find the region enclosed by one loop, and then try to figure out the bounds of that loop. So let's see. So let's graph this in Desmos. We can move it over like that so we can see both. Let me get rid of all of these. All right, so the equation is 1 minus 3 sine. So r is equal to 1 minus 3 sine of theta. So the loop part is, well, it looks like it's this part here. What are the bounds of the loop? Now, the nice thing with Desmos is we can actually kind of draw it. I don't know if it lets us, let's see. So I kind of tricked it, but I'm able to get a slider for t, and I'm letting theta go in between, well, 0 and t. So I can see where 0. So 0 is actually at 1. So it's hard to tell where that occurs, but we can try to make it happen. In fact, it looks like this loop. So I don't know if the image is coming out really smooth or the animation is coming out smooth, but it looks like, and this I could have mentioned before, but the loop part, the closed part of the loop where it starts and ends, happens at this point here, which is just the origin, meaning its radius is 0. I don't know why that happened. Okay. So actually what you can do is you can set r equal to 0 and then see what theta would be. And in fact, I'm going to do that here, and then I'll kind of justify it on with Desmos. But when r is equal to 0, that'll give us our loop. Well, it'll give us possible points for the loop. Well, I guess it really is just the loop. So let's see, when r is equal to 0, we get 1 minus 3 sine of theta is equal to 0. So if we add 3 sine to the other side, we get 3 sine theta is equal to 1. So that sine of theta is 1/3. And then theta would then be sine inverse of 1/3. Let me think for a second here. Now, the issue I see is that so this is like super technical, but the range of sine inverse is negative pi to pi. So negative pi to pi, well, actually negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2 is when sine is 1 to 1. In other words, it's where sine inverse makes sense as a function. And that part's kind of technical, but this is the range of sine inverse.
Okay.
I'm just kind of saying that out loud. Sine inverse of x. But this, again, it's hard to show. But here's what I'm going to do. I'm going to plug these values into my calculator and see what we get. So sine inverse of 1/3. We need to be in radians. I got 0.3 0.3398. And then if you add pi to that, hang on. Something's not sounding right. Okay, so it seems like that makes sense, because when t is, so just to show what I'm viewing here, when t is 0.3398, we see that it actually does pass through the origin. But if you add pi to this, you don't actually get that. Yeah, see, when you add pi to it, it's actually a little further out. It would be actually is it's not plus pi. It is that minus pi. So it's really pi minus 0.3398. And I can show that here. So if I make this a negative, that'll close the loop. See that? Now, the way I'm seeing this, and it's a little, again, this part of finding the boundaries is technical, and it takes a while. But just so we're not taking too long on it, on this part, I just wanted to emphasize that on the actual exam, you will not be asked to find the bounds of integration. So here's what I'm doing, just to show you. So remember, theta is an angle, so sine inverse of 1/3 is an angle. So here, 0.338 radians would be in the first quadrant. Think of pi over 2 as where the first quadrant ends. And pi over 2, if you calculate it as a decimal, is 1.57. So 0.33 is somewhere over there. Now, where is sine positive? Sine is positive in the first and in the second quadrant, right? So in the second quadrant, if this reference angle is to be the same, 0.3398, then sine of this, which is, by the way, this value is just sine inverse of 1/3, will still give you 1/3 when you plug it into sine. But this full angle here has to be 180 degrees, which is pi, minus 0.3398. So again, that part's a little technical. And in fact, really what we can do is just use those values in decimal for our limits. So let me just say, so decimals was just there to justify that those were indeed the values of the loop. And by the way, pi minus sine inverse of 1/3 is about 2.801. I guess it's 0.2 if you round. But I'll just round to one decimal place for each one. So let's just say loop occurs for theta values in between 0.3. I said I would do one decimal place. So between 0.3 and 2.8 approximately. So there we go. So those will be the limits of our integral. So A is going to be the integral from this value to this value. So I hope that's okay. All right, so now what? Well, now what is the equation for the area under the curve for polar? So let me see. So for polar, it was A is equal to the integral between limits of 1/2 r squared d theta. We actually just kind of looked at that was 10.4, so that's kind of recent. So 1/2 r squared. What's r squared? What's r? R is 1 minus sine of theta, 1 minus 3 sine of theta. Squared and then d theta. So the 1/2 we can pull out. And by the way, if you wrote, instead of 2.8 and 0.3, if you actually wrote sine inverse of 1/3 and pi minus sine inverse of 1/3, there's a really nice way to evaluate the end. Like at the very end, you can evaluate it pretty nicely, I think, but it just becomes too long of a problem. So I'm just going to leave it as these approximations, if that's all right. So if we actually expand out this, it's going to be 1 minus 6 sine of theta plus 9 squared, 9 sine squared theta, d theta. I think that's okay. Let me check to see if anyone put anything in the chat. No one's put anything. Okay, good. So now what? Well, now we know how to antiderive each of these. Antiderivative of 1 is theta. Antiderivative of -6 sine is -6 cosine. Actually, it's positive because antiderivative of sine is negative cosine. So the sign changes. The only issue here is what is the antiderivative of sine squared? Well, let's take a look. So the antiderivative of sine squared, if you recall, you would need the half angle formula or the power reducing formula. So remember, sine squared is 1/2 1 minus cosine of 2 theta. Antiderivative of 1 is theta. Antiderivative of negative cosine is negative sine. Since it's of 2 theta, we have to divide by 2. And then there's plus c, but since this is a definite integral, we don't care about the plus c part. And then distributing the 1/2 will give us 1/2 theta minus 1/4 sine of 2 theta. Perfect, so that's what goes here. Perfect. Now, of course, these combine. 1 plus 1/2 is
Don't
3
forget the
halves.
9.
Oh yeah, I forgot the 9. Thank you. Good. So that's not quite true then. Thank you, Morgan. Nice. Plus 9. There we go. Awesome. So this is theta plus 6 cosine theta plus 9/2 theta minus 9/4 sine of 2 theta. Evaluate this between the limits 0.3 and 2.8. And then multiply by 1/2. Now these two combine. Notice 1 plus 9/2 is 11/2. So let me just write that. 11/2 theta plus 6 cosine minus 9/4 sine of 2 theta. Then evaluate. See, at this point, this is actually making me want to go back and rewrite this. So I'm just going to say this. Remember that this was pi minus sine inverse of 1/3, and this was sine inverse of 1/3. The reason why I'm going back to this a little bit is just to kind of show us sine of sine inverse is just 1/3, but the fact that it's sine of 2 theta, it changes things up and kind of screws things up a bit. So again, I'm just going to plug this into the calculator, but I'm just reminding us that there is some simplification that could possibly happen. So I'm just going to use my calculator here. So 11/2 times 2.8, 6 plus 6 cosine of 2.8 minus 9/4 sine of 2.8, well, 2 times 2.8. And again, make sure you're in radians. For the first value, here's what I'm getting. I'm getting 11.17 after rounding for the first value. So you can check to see if you get the same thing, but just make sure you're in radians, okay? For the second value, plugging in 0.3, 11 over 2 times 0.3 plus 6 cosine of 0.3, close parentheses, minus 9 over 4 times sine of 2 times 0.3. So I'm getting 6.11 after rounding here. And again, this is all approximate because we're approximating the limits of integration kind of heavily. But that's fine. So after subtracting and multiplying by 1/2, here's what I got. Let's see, 11.17 minus 6.11 is 5.06 divided by 2 is 2.53. So that's what I'm going to stick with here. I don't know if it made it look easy or not. Sometimes people tell me that you know, when I go over problems, I make it look so easy, but when you try it on your own, it's a nightmare. Try this one on your own and compare to how we did it here together. But it definitely wasn't easy, challenging problem. All right, so now moving on to number 6. Number 6 is honestly, I think, kind of, I don't want to say easier, but the formula is more in our favor, specifically because, again, the bounds are given. But again, for 5, the bounds will be given to you as well for the exam, I think. So let's see, let's move on to 6. So for 6, we want to find arc length. And there are 2 arc length formulas, one for parametric and one for polar. And 6a is a parametric one. We have x is equal to 4t squared, y is equal to 3t cubed, and we have our bounds being in between 0 and 1. So the arc length formula for parametric was the integral between the limits times the square root of dx over dt squared plus dy over dt squared, dt. So just real quickly, to find dx and dt, let's take their derivatives. So to find dx over dt and dy over dt, that is. So dx over dt is going to be 8t by taking derivative. dy over dt is going to be, I got 9t squared. So when plugging this in, still have integral from 0 to 1 of the square root of, let's see, that's 8t squared plus 9t, sorry, no, we're good, sorry. Just thought I saw something wrong. So 9t squared squared dt. Perfect. Let's see, so this is 64t squared plus 81t to the 4. We have to be a little careful here, okay? This problem was easy to set up, but it may be hard to integrate, and here I think it'll actually be kind of hard to integrate. Maybe. So we can pull out a t squared. 64 and 81 unfortunately don't have anything in common, but that's okay. It's 81t squared. I was getting scared for a moment that we may need to do trig substitution, but it doesn't seem like that actually. Now the square root of t squared is just t, so we can pull a t out.
Do like a u sub?
And this is just u sub, yes, thank you, good. This is u sub because if you set the inside equal to u, because that's kind of the natural thing to check first, it's easy to check that this actually works because du would then be 81 times 2 is, what's that, 162? T dt. And since we have t dt here and here, we can solve for t dt by dividing by 162. So 1 over 162 du will replace t over dt. So this is our u sub. Right. The only thing is that the limits will change, but let's see. So we have the square root of u, which I'll just write as u to the 1/2. And then again, t dt, which I have underlined in red, are replaced by 1 over 62 du. 1 over 162 du. When you plug in 0 for t, we get 64. So I'm just looking at this here that I'm arrowing to right now. So when t is 0, because again, our limits are 0 and 1. So when you plug those in for t, you'll see what u is equal to. So when t is 0, we get 64 plus 0. When t is 1, we get 64 plus 81, which is equal to what? It's 145,
Yeah.
want to say? Okay, good. So now we can take the antiderivative. Antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, so multiplied by its reciprocal 2 over 3. That 1 over 62 is still multiplied, and then evaluate between our new limits. It's actually shaping up not too bad. All right, let's see. So there's some cancellation here. We know 162 divided by 2 is 81. 81 times 3, by the way, is 243. Okay, good. And then we have, let's see, 145 to the 3/2 minus 64 to the 3/2. I don't know if 145 to the 3/2 simplifies off the top of my head. I don't think it does. But 64 to the 3/2 does. 64 to the 1/2 is the square root of 64. The square root of 64 is 8. And then 8 to the 3rd is 729. I'm doing all this in my head. But no, you know what? It's not 729. It's 512. I should just use my calculator like a normal person. But anyways, I'm getting this. So 145 to the 3/2 minus 512 all over 243. And that's perfect. Now 145 you can divide by 5 and you get 29. So you can square root 5 or 29 actually. So that indeed does not simplify. You could write it, I guess, as 145. So 145 to the 3/2 is the same as 145 times the square root of 145 if you like. But I think 3/2 power looks a little nicer in my opinion. Anyways, so that was A. So now moving on to B because we still have quite a bit to discuss, and it's almost 10:30. So some of you have to leave by the time we hit 10:30. That's fine, but I'll still keep moving on, and then I'll post a recording on YouTube later after editing out some of the dead spaces, if that makes sense. Okay. All right. So now moving on. Part B is a polar equation. Its r is equal to sine cubed of theta over 3, and our bounds are 0 and pi. So the arc length formula for polar is, well, let's see, it's going to be integral between the limits of this one. I don't remember off the top of my head, but I believe it is r squared plus
dr over d
dr
theta
d theta,
squared.
right? Yeah, there we go. And then d theta. It's r squared, right? It's not r?
Yeah.
Okay.
Dr over d theta and that squared, and then yeah, r squared.
Okay,
plus
awesome. I'm just making sure that this is r squared. But yeah, I think it's r squared. Okay, good. I really should have my book right in front of me, but I don't right now. But anyways, so okay, so far so good, I think.
Yeah.
Let's see. So let's see. What's drd theta? Well, I'm going to use chain rule here. So we have sine cubed. So if you think of that as x cubed, derivative of x cubed is 3x squared. So it's 3 sine squared. The inside stays the same, but by chain rule, we have to take derivative of the inside. Now the inside is sine of theta over 3, because I'm treating r as sine of theta over 3 all to the third. So our inside is this right now. So by chain rule, derivative of that is cosine of theta over 3. And then derivative of that inside by chain rule again is 1/3. Notice the 3's cancel. So really what we have left is cosine of theta over 3 times sine squared of theta over 3. So I hope we followed that. I know that's a little weird. Maybe been a while since we've seen like a heavy chain rule problem, but there's an example of one right there. All right, so that's drd theta, and we have to square it. Oh boy, so things are going to get kind of crazy here. So let's just plug in directly and see what we get. So r is sine cubed of theta over 3. We're squaring that. Plus dr over d theta. dr over d theta is cosine of theta over 3 times sine squared of theta over 3. We're squaring that, and then d theta. So again, easy to set up, possibly hard to integrate. It doesn't look like it's going to be that bad, but let's see. We're going to have to multiply the powers by 2. So that's sine to the 6 of theta over 3. I kind of just want to do a u sub right away to make that theta over 3u. This is kind of bugging me, but that's fine. We get cosine squared after distributing the power, and sine to the 4th after multiplying the power. And notice, what do they both have in common?
Sine to the 4th.
Sine to the 4th. Awesome. So we pull out sine to the 4th. We have sine squared left behind here, and cosine squared left behind here. And what's this?
That's 1.
This is just 1.
It's just 1.
Because the angles are both the same. Sine squared plus cosine squared of the same angles is just always equal to 1 by Pythagorean identity. And then d theta. So all we have left now is the integral from 0 to pi of the square root of sine to the 4th. And since square root is 1/2 power, all we need to do is just half the power 4. To get sine squared. And we actually already did the antiderivative of sine squared. I'm going to use a u sub though. So let me just write this out real quick. So again, just so the inside is u, we'll do a small u sub here. U is equal to theta over 3, which is 1/3 theta. Du is going to be 1/3 d theta. So that means 3 du is going to be equal to d theta. So d theta is replaced with 3 du. I'll pull the 3 out. And now this is sine squared of u. Also, we have to divide each of the limits by 3 to get new u limits. 0 over 3 is 0. Pi over 3 is pi over 3. And remember, the antiderivative of sine squared, we don't have to do the whole thing again. We can just go look back up.
Zoom out a little bit.
What is it?
Can you zoom out a little bit? So,
Yes. Is that okay?
yeah, thank you.
So again, we could go and look back to what we got there. Sorry. But I got, I think it's 1/4 theta I guess it's u in this case. So it's 1/4 u. And then I think it was minus 1/2 cosine. No, it was sine. It was sine. Sine of 2u. But again, I'm going to go back just to compare them. So here I have u, but I believe when we did it previously, we had theta. And it was a little while ago, it was right here. So the integral of sine squared of theta was this. So I have the coefficients wrong. It was 1/2 instead of 1/4 and vice versa. So I'm glad we went back. I just didn't remember it correctly, but that's good. So that's nice. We see part of a problem embedded in another part of a problem, which can possibly happen. And then between our limits are 0 and pi/3. So let's see, plugging in the top, we just get this. Minus 1/4 sine of 2 pi/3. That's going to be the first evaluation. Minus, plugging in 0, that's going to be 0 minus sine of 0 is also 0. So 0 doesn't really do us any good. We get 0 for both terms when we plug in 0. So in total, we get 3 times, let's see. 1/2 pi/3 is just pi/6. Minus 1/4. Sine of 2 pi/3 is radical 3/2. So in total, we get 3 times the quantity. In fact, I guess we could distribute the 3 already. So we distribute the 3. There's cancellation here, but not here. So I'm getting this. I'm getting pi/2 minus, sorry about that, minus 3 radical 3/8. So now, 7 and 8 are 10.5. And 10.5 is conic sections. Now, I'm going to have to zoom in a little bit because it's really hard for me to write small like this. But I can zoom back out later on if need be. But for right now, let me just have it like this. I think this is okay. So let's see, 6 is done. We're going to do 7 now. So 7 asks us to find the foci, vertices, and to sketch the graph. So I'm going to zoom in a little bit, okay? So for A, we have x squared over 9 plus y squared over 25 is equal to 1. And just looking at this, this is what kind of an equation? Is this a parabola, an ellipse, or a hyperbola?
Ellipse.
It is an ellipse. Why is it an ellipse? It's an ellipse because there's a plus in between. They're both squared, and there's a plus in between. If they're both squared and there was a minus in between, it would be a hyperbola. If only one of the variables is squared, then it would be a parabola. Okay? The larger number is under y, so it's vertical. So y has larger denominator. That's how I know it's vertical. Okay. A then is equal to the square root of 25, which is 5. B is then equal to the square root of 9, which is 3. And if we wanted to find C, remember that C squared is equal to A squared minus B squared. So that's C squared is then equal to 25 minus 9, which is 16. So that means C is equal to 4. So to find the foci and the vertices, I'm going to actually sketch the graph first. So I'm going to sketch the graph to help me find these objects. The center of the ellipse, by the way, is 0, 0 because there's no x minus or x or y minus. So that part is pretty clear, I think. Now again, since it's vertical, we're going to go up and down by the larger number 5. And left and right by the smaller number 3. It's really going left and right by the number under x, by the square root of the number under x, and up and down by the square root of the number under y. So we end up with this shape here. Nice. So far, so good, I think. Now the vertices are clear. The vertices are for sure going to be 0, 5, 0, -5. So let me write this. 0, plus or minus 5 for the vertices. And how do you find the foci? You just travel the distance of c towards the vertices. So if this is v1 and v2, then this will be f1 and f2. So the foci I'll label as 0, plus or minus 4. So it's having that understanding that the distance from the center, 0, 0 in this case, to a vertex is a, which is 5, and the distance from the center to a focus is c, which in this case is 4. All right, so that was it for A. So I know I zoomed in, so if you need me to zoom out, well, I'll zoom out later, but I just want to go through these problems so we finish on time. So that was A. Hope you feel okay about A. I'm going to move on to B. All right?
Yeah, that wasn't too bad.
Wasn't too bad. I agree. Good. It's a nice graph, too. So let me write B below, and then I'll zoom in. So B says 4x squared minus y squared is equal to 16. This is a hyperbola. We know why now because there's a subtraction in between the two squares. That's a hyperbola. And it is, what do you think? Is it horizontal or vertical?
Horizontal because x is in front.
Awesome. Yes, it is definitely horizontal because x is in front of the subtraction. If y was in front of the subtraction, it'd be vertical, not horizontal. Good. Now to get it in the form we like, that's the only problem here, opposed to A was already in the form we like. So the form we like is where 1 is on one side. So to make this a 1, we can divide through by 16. There's some cancellation, we get x squared over 4 minus y squared over 16 is equal to 1. Good. Now A is the square root of the number in front, so that in this case is 2. B is the square root of the number in back of subtraction, which in this case is the square root of 16, which is 4. Also, c squared is a squared plus b squared for hyperbolas. So that's 2 squared is 4, 4 squared is 16. So c squared is 20. That means c is the square root of 20. By the way, the square root of 20 is 2 radical 5, because since 20 is 4 times 5, and the square root of 4 is 2, a 2 comes out. So, good. So there we have C. So now we'll start to graph, so hopefully this helps us visualize what's going on. We're going to do the same thing we did for ellipses to get the graph going, but then things get a little different after the fact. So we're going to go left and right by the square root of the number under x. So we're going to go left and right by 2. We're going to go up and down by the square root of the number under y. So we're going to go up and down by 4. Then, instead of creating an ellipse, we'll create this dotted box. Like that. Then we'll look at diagonals which are the asymptotes of the hyperbola. And now, the fact that this is a horizontal hyperbola means we're going to create two opposite-facing parabolas from these endpoints of the box. So like this, and like that. I think that looks okay. Now the vertices are clearly negative 2 comma 0 and 2 comma 0. So I'll write it as plus or minus 2 comma 0 for the vertices. Now the foci are a distance c from the center. So the center of the hyperbola here is 0, 0, of course. So if you travel c in this direction, we'll get 2 radical 5 comma 0. If you travel in the negative direction, you get negative 2 radical 5 comma 0. So where these guys are the vertices, V1 and V2, these points here will be the foci, F1 and F2. So I can just label the foci F as plus or minus 2 radical 5 comma 0. Awesome. So it's a little more complicated than part A, but it wasn't actually that bad. It's super similar, but just a little more complicated because it abides by the rules of hyperbolas opposed to the rules of ellipses, right? Okay. So now part C. So part C says 6y squared plus x minus 36x plus 55. Sorry, it's 36y. Yeah. 36y plus 55 is equal to 0. So now this is certainly a parabola because only one of them is squared. And since y is squared and not x, it is a horizontal parabola. Remember that vertical parabolas are what we're used to, which is y equals a quadratic in x, not a quadratic in y. So kind of keep that in mind. So to get it in the form we like, we need to, well, complete the square with y. So for y, let me kind of zoom in a little bit here. Again, I can zoom out later, but right now this is easier for me to write. For the y's, if we pull out 6, we'll get y squared minus 36 divided by 6 is 6y. And then we need to add and subtract a number to complete the square. And then we have the x and 55, I'll just throw on the other side. Actually, I won't quite do that yet. I'll leave it as plus x plus 55. We're going to need to do that later. So I hope we see what I did. I gathered the y's together, and then I pulled out what they have in common, 6. Yeah, I agree, Martin. The conic sections is literally just an algebra review. There's literally no calculus in this section. It's just understanding how to find these objects. Okay, so let's see. What do I add and subtract to complete the square? It's half of this one squared. Now half of 6 is 3, and that squared is 9. So we're going to add and subtract 9 here. All right. So let me erase this just so I have room for that. Okay, good. So the first 3 we can complete the square with, and we'll get y minus 3 all squared. And then we have that minus 9 lingering there. Now if we distribute this 6, everything else is obviously the same. Plus x plus 55 equals 0. Good. So we end up with 6 times the quantity y minus 3 squared minus 6 times 9 is 54. Perfect. These, of course, combine to 1. So we'll have 6 times the quantity y minus 3 squared. And you expect me to write x plus 1 equals 0, but I'm going to add those to the other side, or I guess subtract those really to the other side. Perfect. So now factoring the negative 1 out, we get this. And then dividing by 6, we get this, which is the form we want. In fact, the form we want for this particular setup is y minus k squared equals 4p times x minus h. So remember that one side is squared and the other side is multiplied by a number. That's how I knew to divide by 6. So in this case, this tells me a few things. It tells me that h comma k, the vertex, is negative 1 comma 3. All I'm doing is looking at what's in front of, not in front of, but what's added to x and what's added to y and changing their signs. Notice y minus k, in this case we have y minus 3, so k is 3. It's the same thing as changing the sign of negative 3 to positive 3 for the y value. Similarly, x plus 1 is the same as x minus negative 1. So if you change the sign of positive 1 to negative 1 for the x value, you get that for the vertex. Also, we get that p is, well, this number is 4p, so p is that divided by 4, which will be negative 1 over 24. Good. Also, notice p is negative, so that means we're going to face in the negative direction. Since it's a horizontal parabola, we'll be facing to the left. So now just to get an idea of what the image looks like. Negative 1 comma
Wait.
3.
Professor,
Yes.
how do you get negative 1 over 24 when it's 4 times negative 1 6?
So 4p is equal to negative 1/6.
Oh, okay.
So if 4p is negative 1/6, then that means p is negative 1 over 24 after dividing by 4.
Oh, now that makes sense.
Okay, good. All right, so the vertex is negative 1 comma 3. We're facing in the negative direction, so it's like this. P is negative 1 over 24. So we're going to actually move to the left. So we're going to subtract by that distance. So again, just so we're kind of clear on what's going on. If this is the vertex, then the focus is going to be over here. The distance from the vertex to the focus is is 1 over 24. So this distance is 1 over 24. So let me move this negative 1 labeling over here. Oops. There we go. So this is 1 over 24. So if you travel 1 over 24 in the negative direction, you'll get negative 1 minus 1 over 24. Negative 1 minus 1 over 24, by the way, is negative 25 over 24. So this is the fraction negative 25 over 24. So then the focus is then the point. So we found the vertex. The focus is then the point negative 25 over 24, comma 3. So same y value, but different x value. Awesome. So that was number 7, A, B, and C. We found the foci, the vertices, and the sketch of the graph for each of them. What's nice is that we use the sketch of the graph to find those objects, so that's good. And now for 8, finally, we're being asked to find the equations of the following. So I don't think this is too bad, but, well, we'll have to see. So find the equation. So A says it's an ellipse. It says the foci are plus or minus 4, 0. And the vertices are plus or minus 5, 0. So this is similar to what we got for the previous example 7a, but it's kind of the opposite. So if you graph this, it'll give you an idea. So the vertices are here, and the foci are here. Since the vertices are 5, 0 and negative 5, 0, I know that it is a horizontal ellipse because the vertices are the ones on the major axis. So it's more elongated towards the vertices, not the other endpoints. So since the vertices lie on the x-axis, then that means the ellipse is then stretched in the direction of the x-axis, so horizontally actually. So we know that this is a horizontal ellipse. And we also know what A is. A is, well, 5. And we know C is 4 because C is the distance from the center to the focus. We also actually know from graphing that the center is 0, 0, but you can kind of tell by looking at it because the other value, in this case the y values, are both 0. So that's a nice suggestion that the y value of the center is 0, but then as it turns out, because of the plus or minus, it's 0, 0 for the center. So let me just write that over here. The center is 0, 0. This is like a side note. Kind of like how horizontal was a side note. Anyways, we know A is 5, we know C is 5. C is 4. C is 4. This will allow us to find B. Remember that C squared is equal to A squared minus B squared for ellipses. So that 16 is equal to 25 minus B squared. That means B squared would then be equal to 9. So B is 3. So the equation we have here will be, well, x minus h squared over a squared plus y minus k squared over b squared equals 1. Now, of course, since this is horizontal, a is under x, but if it was vertical, a would be under y. But now plugging in everything we just found, well, notice since this is h comma k here, these are each 0, so we don't need those actually. So we just get x squared over a squared, which is 25, plus y squared over b squared, which is 9. So the funny thing is we didn't really actually need b, we just really needed b squared. But anyways, there we go, we found the equation. And now moving on to part B. Part B gives us that it's a parabola. And the focus of the parabola is 2, 1. And the directrix is the line x equals -4. So let's see if we can graph this. Well, let's see. Let's go to x equals -4 because that's what's kind of standing out to me right now. So x equals -4 is this vertical line here. Let's just see how many people are left. So still, well, 9 people. I guess 8 people. A lot of people left. Okay, that's fine. And the focus is 2, 1, which is over here. X equals 2, y equals 1. So notice the distance between the directrix and the focus, you can count, but it's 6. It's 4 units to the left and 2 units to the right. So it's 6 units total. So if we half this, we'll get the midpoint between the focus and the directrix on this horizontal line here, which is actually our axis of symmetry. The midpoint is going to be the vertex. So in this case, it's -1, 1. Notice this y value is 1. So we found out that our vertex is -1, 1. And remember, the vertex is h, k. This also actually tells us that, well, a few things actually. We know that, well, we know a lot from this image actually. We know the parabola is horizontal. That's a good note. We know that P is positive because it faces in the positive direction, and we know P is actually equal to +3. Perfect. So now we know which formula to use for parabolas. So it's y minus k squared is equal to 4p times x minus h. If it was vertical, x minus h would be squared and 4p would be in front of y minus k, but it's this way. So this is y minus 1 squared equals 4 times 3, which is 12, times x minus h. Since h is -1, x minus -1 is the same as x plus 1, and I'll leave it like this. So for part C now, we're given that it's a hyperbola with foci 0 plus or minus 4 and asymptotes y equals plus or minus 3x. So let's see if we can figure this one out. This one seems a little hard with the asymptotes are throwing me off. Let's see. Well, let's plot the foci first. So 0, plus or minus 4. 0, 4 is up here. 0, -4 would then be down here. Those are the foci. By the way, the midpoint between those foci is 0, 0, so our center is 0, 0. So h and k are 0, that's good. Also, the distance from the center to a focus in this case is 4. So c is 4, lowercase c is 4. That's really all we know, though. We know it's a hyperbola, so we're going to have some parabolas, but I don't know exactly where the vertex of the parabola lands in between the center and the focus. So I'm kind of at a loss here in the sense that we have to look at the asymptotes now. So let's I guess we can graph. So if you go up 3 and over 1 from the center, you get this line like this. Okay. So this will be one of the asymptotes. And in fact, this is the one y is equal to positive 3x. Negative 3x is the other one. But, well, I don't want this to be that complicated. But we know this, look. So we know that it's going to be a vertical parabola, right? Because it's a vertical ellipse, or vertical hyperbola. So that means A is going to be somewhere here. So let's just call this A. It looks like it's 2, but imagine this is A. And let me erase that 4/3. But that means this point would have to be B in our dotted box. So if this is our dotted box here, then I guess B looks like it lands more to the left, so that's fine. But the whole point is that the slope of this line is b over a, because it's rise over run. The rise is b and the run is a. The rise is a and the run is b. I said it backwards, sorry. So this is a over b times x. So in other words, we know a over b is equal to 3. So it doesn't seem like we learned much there, but the other thing we know is that from the equation for hyperbolas for solving for c, we know c squared is equal to a squared plus b squared. Since c is 4, a squared plus b squared is equal to 16. Also, we just found out that a over b is 3. So if you multiply by b, you get a is equal to 3b. And if you plug that into this, you get an equation for a. I really think this is may not be the only way of doing it, but it's the only way I see of doing it in general right now. And it's a little crazy, but we're almost there. We're like honestly pretty close. So if we plug in a to be 3b, we get this. That means 9b squared plus b squared is equal to 16. So that's 10b squared is equal to 16. So b squared is 16 over 10, which reduces to 8 over 5. I'll leave it like that because remember for the equation, we don't need to find b and a, we just need to find their squares. So we know b squared. And in fact, if we plug this in to this equation, we can actually find a squared. So notice a squared is equal to 16 minus b squared, and b squared is 8 over 5. 16 is what over 5? So 16 is actually 80 over 5. So I'm just writing 16 as 16 over 1 multiplying top and bottom by 5. And that minus 8 will be 72 over 5. Perfect. So that was a little bit of work. Kind of concerned I went too fast there, but I think that's okay. So now, what is the equation of a vertical hyperbola? So we know the hyperbola is vertical. We know the center is 0, 0. So a vertical hyperbola will have equation y minus k squared over a squared minus x minus h squared over b squared is equal to 1. And we know what these squares are. And we know what k and h are. K and h are each 0 because the center is 0, 0. There we go. So in total, we get y squared over a squared, which is 72 over 5, minus x squared over b squared, which is 8 over 5, equals 1. And if you don't like the fractions within a fraction, you can multiply by the reciprocal to the bottom, and you'll get this, which I think looks a little cleaner, but I don't know, maybe I'm biased. There we go. So that concludes C, and that actually concludes the review.